We've seen that different ionic compounds or salts can have acid-base properties when they dissolve in water. In this video, we want to examine whether or not this affects their solubility. So our learning goals are going to be to predict the acidity conditions that may affect or enhance the solubility of a salt. So we're going to motivate this by looking at a real example. Now, I want to remind you that the solubility equilibrium looks something like this, where we've got an undissolved solid on the left-hand side and the ions that it creates in solution as an electrolyte on the right-hand side. We can write down the equilibrium constant for this particular equilibrium as a KSP value. Remember, that's a solubility product, and it's just the multiplication of the concentrations of the two ions raised to the power of their balanced chemical equation coefficients. Now we're going to use lead hydroxide to illustrate this, and we're going to say that this has reached an equilibrium in water, and what we're concerned with is we want to know if it's toxic or not. So let me look at the equation that's involved here. Lead hydroxide is going to split into ions, so it's an electrolyte, and it will create lead 2 plus ions and hydroxide ions. Now these come out in the ratio of 1 to 2 because there's 2 hydroxides for every lead. So I'm going to assign the amount of lead to, I'm going to call that X, I'm going to call the amount of hydroxide 2X. So when I plug these into the formula for the KSP, I'm going to end up with an equation that looks like 4x cubed equals 1.43 times 10 to the minus 20, where the number is the KSP value for this particular salt. Now, when I solve this equation, I would find that X is equal to 1.53 times 10 to the minus 7 molar, and that's the lead ion concentration in the water. Now I want to convert this to grams per liter so that I can do a comparison with the toxicity of lead. So I'm going to take the atomic weight of lead, which is about 207 grams per mole, times this moles per liter to get 3.17 times 10 to the minus 5 grams of lead per liter of this solution. Now I want to use the LD50 for lead in water, and that turns out to be 450 milligrams per kilogram of body weight. So that means that for the average person, I'm going to multiply by their body weight, and that when I multiply that by that body weight, I multiply that by 450 milligrams, and that gives me an idea of how much lead they would have to consume for half of people with that weight to die from that dose. So now when I look at what a toxic dose is, I multiply 70 kilograms. Let's say, average person is about 70 kilograms, about 150 pounds. And the LD50 tells me how much lead would need to be in the solution, and that's 450 milligrams per kilogram of body mass. And now I'm going to divide that by the amount of lead that I actually have in this solution. And that's going to tell me how many liters I would need to drink of this solution in order to get that toxic dose. In this case, it turns out to be 1,000,000 liters. So I probably don't have to worry about the water that this lead hydroxide is dissolved in. That's way more water than I could possibly drink in one sitting for sure. So this turns out not to be a toxic dose. Now let's see how this works with enhancing solubility of basic salts. We're going to consider a slightly soluble basic salt. Now remember, a basic salt is one whose anion, or negative ion, is the conjugate base of a weak acid. So here we have this salt that's dissolving, forming M plus ions and 2 A minus ions in solution, the A minus being the conjugate base of a weak acid. And the equilibrium constant for this, it's a solubility product constant, is going to be much less than 1. This is a sparingly soluble salt. Now the A minus that's produced in solution is going to go on and have a different reaction. That's the base reaction that it has with water. So it's going to produce undissociated weak acid, HA, and hydroxide ions. And we can find that Kb value if we know the Ka of the weak acid that is formed. And that typically is going to be a number less than 1 also. So this is what will happen in the standard situation when we dissolve a basic salt into water. But now what happens when I add a strong acid? Well, there's a couple of neutralization reactions that are going to follow, and they're going to attack the things produced in these two equations above. First of all, we know that the hydroxide ion is going to react with the hydronium ion of the strong acid to produce water, and that has a really large equilibrium constant because this is the reverse of the autoionization reaction of water. So it has an equilibrium of about 10 to the 14th, which is much greater than 1. But we're also going to have some of this reaction happening, where the hydronium ion is going to scavenge the A- ions that are in solution to form undissociated weak acid and water. And again, we know that this is going to be much greater than 1 because the Ka for that weak acid, this is the inverse of the Ka reaction, so this equilibrium is going to be 1 over that Ka. We know the Ka is much less than 1, so 1 over that is going to be something much greater than 1. So again, this reaction strongly favors the right-hand side. Now, the whole point here is the steps we're taking is we're dissolving a small amount of Ma2 in water, and then the acid is going to react with the anion, with the negative ion, to make undissociated weak acid. And the effect this has is to remove that undissociated anion from solution. So now we got to think about Le Chatelier's principle. If we're removing some of the ion from solution, then more of it can dissolve. So in essence, this is how the strong acid can actually enhance the solubility of a basic salt. Let's look at a particular example of calcium fluoride in acidic solution. So I'll remind you that calcium fluoride has fluoride as its anion and hydrogen fluoride as a weak acid. Now, the KSP for calcium fluoride is 3.45 times 10 to the minus 11, so not much of it enters into solution when we try to dissolve it. The Ka for HF is 6.8 times 10 to the minus 4. We're going to need that value also as we figure this out. So the net solvation, this is going to be to combine both the dissolution of the calcium fluoride and the reaction of a strong acid with the products that it makes, will look something like this, where I'll have calcium fluoride reacting with two hydronium ions to make the calcium ion, that's the part that's dissolved from the calcium fluoride, 2 undissociated HFs in aqueous solution, and 2 water molecules. And it turns out now that this has an equilibrium of 7.5 times 10 to the minus 5. So that's a lot better than 3.45 times 10 to the minus 11. So in effect, we have greatly increased the solubility of the calcium fluoride. Let's see how this works out. So when I illustrate, when I run some scenarios, if I dissolve it in pure water, the concentration of calcium ion I'm going to get is 2.1 times 10 to the minus 4. So a small amount. If my hydronium ion concentration is 0.001, that's a pH of 3, it raises my calcium ion concentration now by a factor of 4 over what it was in pure water. If I further raise the acidity to a pH of 1, now my calcium ion concentration is up to 1.2 times 10 to the second, 10 to the minus second. So we've increased it quite substantially from the pure water case. And now if I raise the hydronium ion concentration to 1, so the pH is 0, now my calcium ion concentration is going to be 2.6 times 10 to the minus 2. So we've increased it by a factor of 100 over what it was in pure water. So clearly the strong acid in this case has an enhancing effect on the solubility of calcium fluoride in this solution.